I guess we've started. Hello. As everyone probably knows, I'm Robert, and this is Neptunium. Nice to meet you. If you can introduce yourself a little bit.
Yeah, thanks for having me, Wow. Uh, I'm Neptunium. I do a lot of analytical work and a lot of weird science experiment, and I'm glad to be part of the Wow experiment and all his attempt at the electrolysis and everything he's trying to do. So I'm only trying to bring my little background to help out as much as I can.
You've had a pretty good background, though. I mean, like you've worked with the Coca-Cola recipe and some other cool stuff, right? Or how was that whole thing?
Yeah, this was a bit challenging because I only have instrument I set up at home, like the GCMS. And Coca-Cola is probably not the best one for this particular purpose, but we made it happen. I think Ben from Mass Spec Everything helped along, so we vindicated each other's finding, and I just he does it on a professional level. I do it at home, so uh, the GCMS is good for some analysis, but this one is a bit different. So
Yeah.
but it was interesting. It worked out in the end.
Well, I think I was really happy. I mean, when I heard that you're a part of it, I was like, oh wow, because that was like a really beautiful moment, I think, for like the whole DIY community. Even though it required a lot of work and some other equipment, it's still at the end of the day, it wasn't this high-end university laboratory and this $1 million team that was able to come up with the best Coca-Cola recipe. No, it's just some YouTubers. Just working together and just collaborating and figuring it out. And they were able to, do this thing that a lot of companies probably spend a lot of money. I mean, I don't know if you've tried off-brand Cola, soda drinks, but I haven't. I haven't tried them. I haven't enjoyed them as much as, that recipe that you guys came up with. So, great team by everyone. But yeah, I think again, for me, it's just the, really beautiful thing shows how, sometimes it takes some nerds in their garage to figure it out.
Yep.
Um, but yeah, so that's Neptunium. Again, he's someone that has a experience that I desperately need. And am growing on also, and that's analytics because when I first started with this mining technology, same thing with me, right? Like I started off with using this kitty litter box, and I like hot glued my membrane in there and like used some silicone pipes and stuff, and it was absolutely horrible. It was, completely horrendous, but it worked. It worked, and I scaled that up to this other prototype thing, uh, and I was able to process 70 pounds, right? I went from absolutely nothing to processing 70 pounds of material in only a couple months. It was a little less than 3 months. And then
I've
from there, and then from there, I spent a whole year, right, trying to figure out what do I do with this material I produce because I electrolyzed it, I leached it out, I produced this concentrate, and I did a stannous chloride test. So I knew there was something, right? I knew there was some there must have been some sort of precious metal because I did a stannous chloride test, and that's a pretty reliable test. There's some acid dilutions where I used, let's say, nitric or other acids to try to separate the base metals, and I was able to refine it, but what do I do with it, right? And I spent the next year trying to find a laboratory or refiner, someone that can actually buy it and separate it properly to each individual element. Because, what I then learned is, oh, there's companies that will buy platinum or they'll buy rhodium or they'll, of course, lots of people will buy gold. But the platinum group metals is just really, really hard to deal with thing where it's you're lucky to find maybe a refiner that'll can separate like two or three of them, but try to separate all six of the platinum group metals, and especially if you mention it comes from ore, they'll just hang up on you. They won't even talk to you because when you're dealing with ore, you're dealing with 20, 30, 40 different elements that you have to try to separate, and it's just a headache. It's a headache. And then the analysis, I realized, oh wow, so also the analysis that just doesn't exist, right? I've tried so many laboratories, and I thought, okay, it's just me, right? I don't have the experience. I'm just some kid in my backyard, right? I don't know what I'm doing. But then I started getting in contact with really large mining operations, these global multi-billion dollar operations. And they were saying the same exact thing I was experiencing, that there's just no analytical services. Because fundamentally, and a lot of people might hear this that don't have the experience. So they don't understand. Right? They're like, how does that work? Right? There must be someone. But the fundamental problem is there's no mining industry in America, right? For platinum group metals. Because there's no mining industry in America for platinum group metals, there's no analytical services, right? Because why would there be a laboratory that specializes in analyzing for PGMs if there's no industry to, support it off, right? And if there's no industry that produces any platinum group metals, why would there be a refining industry that supports it? You know, we
Yeah,
have
exactly.
we have a catalytic converter refining industry, but that's for catalytic converters, and separating a catalytic converter, which is a very controlled, thing that might have less than a dozen elements, is way easier than raw ore where you're trying to target in the parts per billion. Um, so anyways, all this, I'm like, okay, this is a struggle. And my whole dream, my entire life when I started was to have a handheld XRF. I'm like, if I have a handheld XRF, I'm set. I have everything I need, even if it's like, sure, maybe and I might be able to get to the, parts per million or whatever. But if it can get to like, if it's like 10% accurate or that, I'll be happy. And then one of my biggest learning lessons is it's not 10% accurate. It's basically 100% inaccurate. And I think that's like what, if you can talk a little more on that, like I feel like this is a thing that all professionals, especially people also people in the mining industry, when they have the proper experience, but like all professionals, you ask them about this, they're like, oh yeah, no, XRF it sucks. XRF it sucks. But no one, like if you most people you ask on the street, or especially most people that are interested in mining or whatever, even a lot of YouTubers, they'd love to have an XRF. They think, oh, XRF is great, but everyone would experience and knows it. Like, what? How does this exist? How does all the professionals know about this, but the rest of the world doesn't? Like, how did what?
So XRF is great and it's very helpful if uh, if you can use a uniform sample, right? So it kind of pinpoints the area you want to analyze, and because you're dealing with minerals, they're usually not uniform on that level, right? So uh, XRF is great if you have again a uniform sample. If you don't, well, it's going to give you hit and miss results. Uh, you need to uniformalize your sample. Uh, uh, that's why it gives you hit and miss results. And for quantitation, it's also not great. It's decent for qualitation. It tells you, well, there's some of that in there, but there's some of this too. How much of it is? What's the difference?
So
So
could you explain what is the difference between quantitative versus qualitative?
so uh, what's in there is qualitative. How much of it is quantitative? So you could do two things. Tell the customers who wants an analytical report what's in there, and you give them, hey, there's this, and this. All right, great, but how much of it? Well, you need a quantitative method. To do that, you need to have a standard and inject incrementally higher and higher concentration to establish a calibration curve. So you can tell, oh, okay, well, if it matches this signal I get from this concentration, then I can tell there's this much of it in my sample. And on you go. If you don't have a standard, you can guesstimate based on the signal you get from the instrument, how much is in this sample or how much isn't. Well, comparatively, you can tell, well, there's a lot of this and very little of that. But that doesn't really tell you much because you can get a really strong signal from a tiny amount of, I don't know, uranium on ICP-MS versus a really weak signal where of thorium when you have a lot of it comparatively. So it you need a standard to establish your baseline and tell, okay, well, if I inject this much, I get that much. If I inject this much, I get this much, whatever.
Yeah.
So the
I
quantitation is important, and XRF kind of missed that a little bit. So
Well, one thing that I find interesting is if you ask all these manufacturers, because when I went to before I purchased this this equipment, right? Like I made sure to do my due diligence. I didn't just because like the person that was funding me, they really wanted a handheld XRF, and again I didn't know what I was doing, so I was doing my best to research as well. And one of the things I did was contact a manufacturer and speak with their engineers. I asked them, hey, can I have a call with your engineers? I want to learn about its application directly for what I'm trying to do. How exactly would it work? What are its downsides? And the consensus with all of them always is XRF requires a calibration sample, right? It require like for example, if you want to analyze it on your ore feedstock, you can't just put it in the machine, analyze it, and be done with it. No, you have to get that sample, sent it to a person like you or other laboratory that can properly analyze it, get an ICP-MS analysis of the full digestion, the whole proper full digestion of that specific ore matrix and that specific ore stock. Then once you have that, then you can create a custom profile on your machine for your custom ore, for your specific ore matrix. And then you can run other samples, like you said, right? Once you have that, understanding that, then you can compare the differences from that, standard. But that's the biggest problem. Even I abuse my X, and when I say abuse, I don't use it properly, where I'll just click all the elements on the periodic table and analyze it. Why? Because I don't know what's in there, right? That's the fundamental problem. But because when I do that, there's overlapping peaks and noise in the data and so forth, and that creates false positives and so forth. Um, but yeah, I think you said it perfectly, where doing analysis requires a lot of work. It's not something as simple as you just put it in a machine and you get numbers. Numbers don't mean anything. The spectrum is what matters, and properly analyzing that spectrum, properly working with it, that's an art, right? It's a dancing back and forth. At least with XRF, that's how I see it.
right. Uh, I give you an example, and I'm sure people already know watching this. Maybe not. Uh, you XRF something that's uniform, right? It's all the same everywhere. Let's say you put some salt in there. Well, sodium is not going to give you a big response, but if you have a tiny amount of iodide, it's going to pick it up strong because iodine is a much bigger atom, and the electrons respond a lot better to XRF than sodium would, because sodium is a tiny atom. So right there you have a discrepancy. So you can tell, oh, well, there's a lot of iodine in there. But no, there isn't. It's just mostly sodium chloride, and you get a tiny peak for. But that's just because the XRF is more responding to higher atomic weight samples, units, whatever. uh, for any other instrument, it's the same thing. ICP-MS is better with higher atomic mass. It's more sensitive to higher AMU than lower one. For the ICP-OES, if you want to go there, it's more sensitive to the emission line that whatever something is going to emits on. So boron has some really high lines, but copper have some lines somewhere around there too. I'm not too familiar with OES as much as MS. So you get some description. That's why you need a standard to, hey, okay, all right, here's a calibrated standard made by a reputable company that guarantee that you're going to get this much in this bottle. If you injected this much, you're going to get this response guaranteed, plus or minus XYZ radio. All right. Oh, you injected, you get this response. That's your calibration mark right there. And then you can do dilution from there and see how low you can go for detection. The problem with mineralogy and the things you're trying to do is you don't know what's in it, so you don't know what they're calibrated for, and you bump into this problem like, well, what if there's arsenic in there? Am I trying to quantify that? Am I not trying to? Is it going to interfere with copper? Is it going to interfere with the line from boron or other elements? I don't know. I don't know what's in there. There's a lot of stuff. It's nature, right? It's always a mixed match, a bunch of stuff. That's why I think personally the ICP-MS is the instrument of choice because you select per isotope. So it doesn't matter if you have a, a crap ton of copper interfering with uranium. It doesn't matter because uranium is so far away from copper. Uh, it's unlikely to interfere in any meaningful way. Uh,
So what's the could you go a little bit more into that then? Explain, ICP, I guess. How does it compare to XRF, for example? Like how do you actually get a sample, prepare it and analyze it through, ICP and also the different types of ICPs?
so with XRF, you could just put your sample wherever it goes, have it XRF bombarded with X-rays, and you can tell, okay, well, based on where the X-rays land, you can tell what's there. But if it lands a few millimeters or even a few micrometers away, it can get a completely different results because you're in a ununiform, not uniform matrix, right? So do you have a discrepancy here? Because okay, it's non-destructive, but you, you're dealing with non-uniform samples. ICP, OES, or MS, you have to digest the samples. You have to put in an assay that's going to hopefully dissolve everything that's in it. I say hopefully because I know you're dealing with precious metals, and sometimes they don't care. They don't want to go
Yeah.
in uh, in the matrix in the acid. So you have to have some more aggressive method to dilute it. Once it's in solution, let's assume everything goes into solution. Now you have a uniform sample. Everything is all in solution. It's all uniform. And you inject that into the instrument, either the OES or the MS. If it's the OES, then you're looking at the emission spectrum once it go into the plasma. And it's going to have a really specific emission lines. And these are very well known, and we can tell very close by emission lines. The instrument is able to separate them very efficiently. So there's little interference, but they can't tell if it's a different isotope or anything. The MS does the same thing. It's kind of like a small particle accelerator. It just, instead of going into the plasma, emit its light and being sucked by the exhaust fume hood. uh, it, the uh, uh, the injected samples goes directly inside the instruments and is accelerated inside a vacuum towards a detector past a bunch of uh, 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 magnetic and electric field. So then you can separate it by mass. You can get rid of all the stuff you don't want and only get this one mass you're interested in. That's why the isotopic ratio is important in that case. Uh, uh, that way, you can really focus on one particular thing. Now, if you have isobaric interference, you have a problem. But how many times are you going to have these isobaric interference come into play to interfere with your signal and give you a false positive? Fairly rarely. It's not
Well,
like
what do you mean by that? Could you explain what does that mean?
so. For example, if you try to look at strontium and its isotopes, strontium has stable isotopes at mass. I think it's 87, if I'm not mistaken. If you want to compare this with rubidium, uh, they both have stable isotopes at mass 87. I think so. You have to know your sample where it's coming from to determine if am I looking at strontium, am I looking at rubidium. Rubidium is not that as common as strontium. Strontium is pretty common. So if you have a strong signal, it's probably a lot of strontium. If it's a natural stuff that you come up with, rubidium, it depends. If you get a sample that's from the bottom of an ocean, it might have more rubidium than strontium. If it's from a Dian Sea, like the Caspian Sea
Yeah.
or the Aral Sea, it might be more strontium. It all depends where it comes from. You have to know where your sample is coming from, but it's fairly seldom and rare, so you don't really have to worry about it. Especially the precious metals, they do have some interference with each other and with rare earth, but
Well, no, I get you. I get it. XRF has a very similar problem, with like, for example, lead and iridium. In fact, a lot of XRF equipments, they have iridium just completely disabled because the peak for iridium and lead is like right next to each other.
Right.
It's, it makes it very difficult to operate. So no, I completely understand what you're describing. Although having the same exact mass is sounds even worse. But so what about, I think for that, the most important thing is firstly knowing, the equipment, right? Knowing what those, interferences might be so that when you do see them, you can identify them. Like in my case, right? If I see that there's, if there's any form of lead in the sample, because there are also going to be secondary peaks for lead. If I see there's any sort of lead in the sample, I have to completely discard any iridiums and either do specialized separation, right? I'll either use selective acids that dissolve the lead but not the iridium, or better case situation is to use a different equipment. So, would that would does IC would be able to utilizing a ICP-OES with an MS, for example, clear up a lot of those interferences? Or, I know XRF can't get to those accuracies, but even, using XRF, right? Using multiple different equipment to be able to tackle that problem from a different angle. So pretty much using ICP, MS for, or ICP for target analysis, and then using different types of ICPs to, then separate the different types of interferences.
Well, so the XRF is not that bad to give you a rough estimate what's out there, like a paint a really wide brush paint out what's out there if you have a uniform sample. Then after that, you can try to digest it and put it into the OES and see what's roughly in there. The OES is never going to be able to get down to the part per billion and low part per trillion like the MS will. And then there could be interferences because you don't know what you're looking at and what's possible in this sample. The MS is able to steer clear of all this stuff and give you a better picture and down to really low level. Now, you don't want to overwhelm it. By that, I mean, you don't want to look at, say, calcium or sodium into a sample with a ICP-MS because you're gonna blind it. It's like pointing a telescope at the sun, right? The telescope is meant for really dim light, just like the MS is meant for really trace metals. You don't want to point it at the sun in the case of a telescope. It's so bright, you gotta fire your detector, right? So that's kind of
What
the analogy.
what solution is there to that, right? Like, let's say I do have a digested sample and there's a lot of calcium, which of course in my case there is going to be, right? Because I'm dealing with a lot of ore. What solutions is there? Is there simply I have to selectively first remove the calcium mostly? Would diluting the sample work? Though the problem with diluting is obviously, you also dilute the precious
Well,
metal analysis.
well,
Like
it,
what
it depends. Are you trying to quantify calcium or you don't care? If you
I
don't
don't
care,
care.
you just don't look at calcium. It's just that simple. On the software, you tell
Okay.
them, hey, don't look at mass 40, 44 because that's where most calcium is. And I don't care about that. So don't look there
Okay.
and just look beyond that. If you're interested in titanium, which is not too far away from that, and look at that instead of looking at calcium. You know,
Okay.
let me see.
Well,
Calcium, titanium is around 47. So yeah, okay. Just look. Am I reading this? Yeah, 47. So instead of looking at 43 or something. Now, if you're interested in scandium, it's really close to calcium. It's the next one right on the periodic table. So you may have some interferences because isotopic calcium has a bunch of isotopes that could interfere with it. But if you select a specific isotope of scandium, you can stay clear of all that crap. And there's different method to make sure that you stay clear of all this because it's so close to it. You're looking at really close to the sun in the telescope analogy, right? So you want to blind the sun and just look really close to it, and you'll be fine if that's really what you're interested in. But
what about doing so firstly doing a first analysis ignoring the calcium, for example, right? That way you get all the trace stuff, and then you dilute the sample and then retarget the stuff that was blinding you at first. Would that work?
so yeah, let's say you're interested in tungsten, right? You have ppm level of tungsten, and you want to know exactly how much tungsten is in there, which is likely to happen in uh, uh, precious metal samples. Yeah, you do a dilution. That's the way we usually do it. Well, okay, we got ppm level of tungsten. Okay, well, the ICP-MS is going to give you a reading in ppb, or your calibration curve is up to 100 ppb at most, but you got 1,000 ppb. What do you do? Well, you just dilute it 10 times and measure it to make sure it fits that calibration curve. So if you calibrate from 0 to or 1 ppb to 10 ppb, what do you do? You do a first measurement, you get 1,000. Okay, well, dilute it 10 times or 100 times. And then do a measurement again.
Would trying to measure it, if you, let's say you don't know, right? So you try to measure it and it's too high, would that damage the instrument?
Uh, Not at first. Over time, it will. The detector only have a lifetime of so long. If you do it
Yeah.
repeatedly, yeah, eventually you're gonna have to. But it's a normal lifetime of
Like how many runs would that be, for example?
uh, I've
Couple
worked.
dozen, couple hundred, couple thousand?
So I worked in environmental labs before where we had this type of situation where, hey, I don't know what's in it. Tell me what much sodium is in there or silicon is in there, and
Yeah.
they give you pretty much a bucket of sand. It's most of it
Yeah.
is silicon, right? So
Yeah.
a lot of dilution. Okay, all right. Well, the first runs after 1 million dilutions, giving you 10 million counts. Something absurd. So okay, you do dilution again and again, and this instrument was run every day for weeks on end. After about 2 years of that, you get to a point where the detector need to be changed.
Okay,
Uh,
so it's not nothing crazy though. Because the reason I asked is because I remember there's one. I was able to find. I remember during my couple of years, I was able to find one laboratory that specialized in analyzing platinum group metals, but they were in South Africa. So I had to send my sample to South Africa.
that
But
sucks.
yeah, well, because again, right, that's the only place there's a mining industry, which makes sense. But this top laboratory, I was asking because I wanted to send my concentrate, which of course isn't in parts per billion. It's closer to probably in the parts per thousands or millions, definitely at least. But I told him I'm like, can you analyze? Oh no, we can't. Because we need our the concentrations to be like you said, right, it needs to be below a certain amount. And I'm like, okay, can you just dilute it? And they're like, no, no, we can't do that. And I'm just like, what? I'm thinking like I mean again it's one of these things where I'm okay with admitting I don't know what I'm talking about, but I assume a laboratory can do a dilution. Is that not difficult?
Yes. No, I don't know what they were smoking there, but that's usually what we do. If a customer show up with a seawater and they want to know exactly how much sodium chloride is in there, well, I'm sorry, but you're gonna have to do a dilution. It's gonna skew the results to a point because your dilution is only going to be that good, right? But you're going to be able to give them results. You can't just run that straight on an instrument that measures part per billion in something like seawater that has what 5% sodium chloride.
So how do they do that? How do they measure gold in salt water, which is in the parts per trillion? I've seen these studies. I've noticed these studies are sort of old, where like there aren't really many recent studies that like kind of do this. Like why like how would you imagine that would look like?
I would probably assume CPMS is the way to go. I mean, I don't.
But with the sodium, like how would wouldn't you have to dilute the
Oh, no,
sample?
no, no, no! It doesn't matter. You're not looking at sodium. You're
Oh,
only
you just
looking at
ignore it.
gold.
Okay, I
Yeah.
forgot.
So you're looking at gold at mass 198 something somewhere. So mass 23 for sodium doesn't matter. You never look at it. Just
Yeah,
like a
yeah, yeah.
telescope, right? You don't point it at the sun. You point it at somewhere dark to see what's there. But you never point it at the sun because it's so bright. So imagine the whole sky is your sample. You have sodium is the sun. You don't point the telescope at the sun. You just point it somewhere else, and you get to see really, really dim stuff. This is the
Mhm.
same analogy, kind of. You know what I mean?
Yeah, well, I mean that definitely answers it well. Yeah, it's just one of those things. I mean, a lot of people I think they think
And
it's
I,
really easy just
and,
go.
and I think that's the power over OES. The OES is simpler.
Uh-huh.
It's easier and it can tolerate really high concentration stuff.
Mm.
The detector in the MS is more sensitive, so obviously you get to see lower stuff, but you can't bombard it with high concentration crap all the time because you'll destroy it. But the OES is different. You can uh, put something highly concentrated and because all you're looking at is light. So if it's a really bright light, it can only be as bright as uh, the detector can tolerate. So
Mm.
that's one thing, but it's not as sensitive, and it's
But the
uh
detector is replaceable, right? It's a
yeah,
consumable. Okay.
it is, and it's built in the the contract when you buy a new ICP-MS. Tell you, oh, okay, well, you replace the detector in like a year, 2 year, 3 year, 5 years, whatever, however you use it. So it's built in the options, and it's the preventive maintenance. Tells you have other options, right? If you don't use it as much, you can also increase the voltage and the detector to get uh, decent feedback from it.
So what do you think about used ICP equipment? Have you looked into them at all, or what are your thoughts on that?
What do you mean?
Like used just have you looked into like they're buying used ICP equipment on eBay and stuff? Or
Yes,
what
yes.
do you think it's not worth it, or what are your thoughts on that?
Uh, so ICP-OES and ICP-MS, they're greedy. They use a lot of argon, right? They're greedy
Mm,
at argon. So you need a lot of argon to feed them. But now, if you're only using them for sporadic experiments and analysis here and there, a tank of argon is okay, but a huge tank, a 300 cubic feet, the biggest tank, single tank compressed argon, is fine because once you're done, you can just turn it off. You're done. Well, the one I'm used to use at previous lab is it's a duor, so it's got many gallons of liquid argon in it, and it lasts a month because we use it every day. But if you don't have that kind of use, you can use a single tank, and if you use continuously, you can get 10 hours out of it, maybe 12 hours out of it. Yeah,
wow.
it's really greedy. It's so you gotta.
So how long does a sample require to analyze? Let's say I want to run one sample. How long would that take?
Well, if you have it, so if you run one sample, well, you want to know what's in it, right? And you want to know how much is in it. Well, for that you need to do a calibration. Okay, great, but to do calibration, you need to tune the instrument first. To do all that, the tuning, the calibration, and running a sample isn't going to run but a few 100 pounds, maybe less, of argons in the tank. So you might be able to get away with it and then shut it down, cut off the argon, and you might be able to do this a few times before a single tank ran out. But it's still going to go fast. It's a greedy, it's an argon greedy instrument for sure.
Okay, so I mean that's definitely a lot. I won't I won't deny that definitely a lot. I'm trying to think of options like like turning it on or off, or between runs and stuff, or even having it automatic, like because I know like this equipment there's a wavelength dispersive ICP, and it requires a like the specialty, I forgot the mix of gas, but it's like um I think like methane and CO2 or some weird like thing like that. I forgot, but it's for the detector, but it's very, very small. Like I actually left it on once, and like I came back and barely used any after a couple weeks. But obviously that's a huge thing, right? But this thing doesn't have an on-off valve on it, which is kind of annoying, right? I have to manually turn it off. Like, is that the same thing with the ICP machines? Do they automatically have a on-off? Or is it I have to manually turn it off every time?
Uh, no, you can set it up when in the software. Once you're done running the method and the samples, hey, go to shutdown mode and it'll shut down. Then you got to remember to turn off the valve, right?
Okay.
But
So all right, ignoring, argon thing, let's say we have, we don't care about argon, or let's say, we're not going to run too much. Getting one of these ICP equipments on eBay, like I've seen some of them, um that they go for like 5-10 grand each on eBay. um and obviously some of them are as is, not condition. I've seen them for like 25-30 grand, like refurbished, and sometimes even with a warranty, like completely recalibrated and everything. uh but again, right, like buying something for like 5-10 grand, and do you think that can be something that can be churned into a working machine, or is that something that just requires a lot of time and effort to actually get into some working?
No, well,
Because from
it,
what everyone I spoke to, that has experience with rebuilding these ICP machines, they say it's a very simple machine, right? There isn't much to it. Unlike, one of these things where you have very expensive crystals that if they slightly get oxidized or whatever, they go bad. You have a 4 kilowatt X-ray tube that, has 20 different issues that can go bad, and trying to rebuild that is, a brand new X-ray tube is like 20 grand. Right, there's a bunch of things that can go bad on this, and trying to replace it isn't fun versus an ICP where like they have consumables, and you know
well, you went into what kind of instrument you're getting, is how bad a ship is it when you get it, how old it is, if it's super old, how much trouble are you going to get into to trying to get replacement parts for it that's been obsolete for 20, 30 years. I don't know. It's my experience with GCMS and LCMS. The the stuff I have at home is it's already difficult to find parts. I mean, I'm lucky if I can find detectors for sure,
yeah,
but so I bought a few of them, so I have different parts from different instrument. I can sweepy swappy uh,
yeah,
between each of them to make one work out of, I got four, I think.
yeah, yeah.
It,
How old was
it,
your two questions? How old was your instrument, and what brand was it?
uh, the GCMS is so it was made of Finnegan before Thermo bought it. So it's a Thermo Finnegan. At the time, I guess they were dealing with each other's, buying each other's company or whatever, but it's supposed to be a thermal stuff because the software I think is thermal only, but the instruments say Finnegan thermal. So it's, again, you're dealing with a time where they buy each other's property companies, who makes what and who's. I run into this at work all the time. Like, hey, I have this instrument. We have a problem. Call this. Oh, no. You got to call these guys. Okay, you call these guys, and they refer you back to the first one. Oh
Yes,
no, that's this guy. Just deal with this guy.
yes.
So,
I
so
had the same problem with this thing. I
right,
was trying to buy the anode tubes, and it's like a Toshiba X-ray tube, but Toshiba doesn't make X-rays anymore. That division got bought out by this company. I called the company, and it's yeah,
exactly. Yep,
it's a headache.
exactly. Yep.
Well, I mean, I hope, I hope I can, and obviously I definitely would like to get you also one. If you want to run that much argon, I don't know. We'll see. But, yeah, I mean, it'd be nice to, because I see it all the time, these machines working. And, the reason I ask what brand is because, what I've heard from a lot of these people is like Thermo Fisher. Of course, in your case, that's a rough situation, right? They're buying out a company, and so that it's always that time period is the worst part too. But yeah, like with Thermo Fisher, what I hear from everyone is they have the best, in terms of support, right? Like, Agilent, or for example, everyone else, like especially Agilent, like every single person I've talked to that had an experience, like, is like stay away from them by 1,000 miles, because you know, I mean, their equipment's great, right? It costs a lot of money. It's nice, but any sort of after support, from what I hear, is really difficult, and it's very expensive versus Thermo Fisher, where a lot of times their older equipment, they'll give you upgraded software completely for free. Which is completely unheard of, right, scientific analytical equipment
Yeah,
um
I don't want to get too
company. Sorry.
yeah. We are in the different time nowadays because companies start drifting, especially after COVID. They start drifting into more and more remote access computers. So they want your computer attached to the instrument to be remotely accessible from a company at a distance, right? So they want to, oh, what's your problem? Well, let me fix that at a distance, so I don't have to send somebody else, especially if your instrument is in the radiologically controlled area or some place that don't want to send somebody to have a background check to get into or whatever. So let me see what's your problem. Oh, okay, you got this and that. Recently, though, I just set up an instrument at work, and it sounds like they want to go towards what Netflix, Amazon, and whatnot is going through is repeated subscription, right? So you have a software to run the instrument, but as soon as you stop paying for the subscription, it's gone. You can't use your instrument anymore, so
Yeah.
you have to pay again. So it's a I don't like it at all, and
I mean,
it's
it's an issue across all industries, right? You know, farming from farming tractors to,
yeah,
you know, high-end scientific analytical equipment. No, I
you're
get
right.
that. I just hope that, you know, you know, eventually I'd like to, you know, see a DIY, you know, ICP or, you know, open source ICP, an open source, you know, XRF, open source sort of thing on. Definitely XRF though is, I looked into it. I looked into trying to build my own XRF, but the problem is the solid state detector. That requires like this really complicated thing. There are other detectors available, but, you know, fundamentally, you know, XRF, XRF, right? If you're going to try to put all that headache, you might as well try to DIY some other sort of instrument. But you know, I definitely would like to see that. You know, I'd like to see that shift and, you know, somebody doing that because, you know, as much as I'd like to do it, I can't do everything. And you know, maybe I don't know, maybe eventually I'll you know, I don't know, maybe I'll be able to find a team and then, you know, just open source and analytical equipment because I can't stress it enough in the mining industry, you know, it's like everyone I talk to, everyone's, you know, seems like, oh, this must be a super easy thing. Well, you know, why is this so difficult? But, you know, for people like me and you, we get it, right? You know, we've been through a headache and we understand the science behind it, how it works and why it's so difficult. Um, but also it doesn't have to be. You know, it really doesn't have to be difficult, right? Like same thing with XRF. You know, if you prepare the sample properly, it can get pretty reliable. You know, I've seen it all the time where like I analyze a sample with, you know, directly and it doesn't show anything. And then I run it through one of my mining units or whatever, and I separate it out into a powder or whatever, and then you can actually analyze and see gold, right? Like I sent you earlier today. Um, or
Yep.
in other cases where, you know, slag, right? Like you just analyze the ore directly and you don't see anything. But if you analyze the slag, because the slag is that homogeneous, right? Like that, you know, it doesn't have you know, pinpoints where like this part is this and this part. No, it's completely, it's a glass structure, right? It's completely
Because it was melted, right?
exactly, exactly. It's completely, you know, it's a glass, it's a, you know, it's a glass, right? A scientific term of a, you know, perfectly homogeneous, you know, mixture, right? And that analyzes so much better and that shows very much more accurately and you can see much better you know, on the spectrum curve, a much better results. You know, so I don't know, I feel like it'd be nice, you know, that this is a really huge industry opportunity, you know, being able to provide really, you know, easy and rapid and cheap analytical equipment. I really feel like that's an opportunity that someone one day, maybe one of the people watching this, you know, they put in the time and effort to try to do it. All it takes is one person.
Yeah. Um, analytical instrument is always difficult because it's tied to big corporations. Uh, that's why uh, at home, me personally, I only use old equipment I found on eBay, but uh, it doesn't make them less functionable. Like they're still pretty functional. Um,
Yeah, I've looked into the ICP OESs, for example, like, you know, there's not much in terms of like, you know, last 1 or 2 decades, right? In terms of them, they're pretty much the same. They're pretty consistent. But the ICP-MS is like, you know, you know, if one day, you know, I do win a really big grant or whatever, I do can get the dream lab I do want. Like an ICP-MS is something that I would really want. Have you looked into that at all? Like the latest things that they've come up with to try to like fix those, like you were talking about earlier, the mass. you know, try to better identify different elements. Have you heard or looked into that at all?
uh, they came up with different method to get rid of isobaric interference. Ultimately, you're kind of screwed because you're looking at, let's say, for in a uh, strontium and rubidium example, you're looking at mass 87. Okay, well, 87 point what? Point zero. Okay, but they're both rubidium and strontium still have 87.0. Okay, so how deep down you want to go? Ultimately, you need a high resolution mass spectrometer, which is something as big as maybe half of my house. So, the same kind of equipment they do carbon dating with. No, it's you're not gonna get it, and it's not worth it really to do this. What you can do is, instead of focusing on that, you can do a preparation well. You can tell, well, the sulfate of strontium is pretty insoluble versus the sulfate of rubidium is soluble. So I'm going to treat it with sulfuric acid, and you get rid of all this interference. And the story.
Mm.
If that's what you really focused on, then you can do that. Just and you don't need super expensive equipment to do that stuff.
Do
So
you see any sort of interference possibilities with like the work I'd be doing, for example, with, I mean, the two primary groups is of course the platinum group metals and then the rare earth elements. But, I would also like to do all other critical minerals and, like gallium and germanium and also some of the alkalis like, cesium and lithium. Lithium can't be done on ICP, right? Or can it?
yes, yes,
It can? Okay,
yes.
awesome. Okay, great.
Yeah,
So,
that's just the lowest you can go. We do lithium actually on ICP-MS at work. It's not an issue. We do beryllium too, so it's not
okay,
a problem.
perfect.
All the way up to, well, I think this one goes to mass 300 and something. So you can do actinides beyond plutonium, but beyond americium, California, you can do all that. That's not an
Yeah,
issue.
no, I don't touch anything past uranium for obvious reasons. All of that is synthetic. So,
No, no, but
no,
it's
no.
it's it's possible to do that.
Yeah, yeah, yeah.
The MS is usually more sensitive to higher masses because they yield a bit, a higher signal because it's mass to charge ratio. So given the same charge, the masses is what matters, and a higher mass at the same acceleration voltage is going to give you a better signal than a tiny mass like lithium. So yeah, you can do Einsteinium fermium if you have it. If you have a standard for it, you can even calibrate for it.
So do you other than what was the example you gave? Rubidium or you gave rubidium, right?
Yeah, rubidium and
Okay.
strontium 87. This is a notorious one. A lot of
Any
people
other
from
examples that you can think of in terms of critical minerals, rare earths, or I'm
yeah,
not sure.
yeah, all the lanthanide have overlapping masses. On top of my head, I can't remember which one is samarium and
So the
uh,
rare earths, good luck.
yeah, europium. All these guys, they all, not all of them, but they all have.
How bad is it? Is it like to the parts per billion, like, or is it? Can I like get at least to the parts per million with them?
We have to go on case to case basis. I don't know on top of my head how many isotope of samarium interact with how many isotope of europium. I don't know, but I have to look at it, and I could tell you exactly. Well, in that case, you could go, well, let's say europium. Which one is it? 153, 150 somewhere in the lap with samarium 150 something. Well, you just look at another one. Instead of 152, you look at 153. Instead of, you can select which isotope you want to look at. And that way you could get rid of all this stuff.
Well,
The
the reason why for me I'm asking, because doing rare earth separation is something I'll have to get into, right? Like that's, I'm not, are you familiar with like how, I mean, you probably can guess at least how difficult it is to separate the rare earths, right? They're incredibly notorious. And, I would like to, be able to experiment and optimize that. Like, one example I get a lot of people recommending me is, using pulse width or, trying to do certain frequencies or, also I'd like to develop selective ion exchange membranes. I can selectively separate, selectively selectively select. Is that I don't know if that's a word to put together, but yeah, selectively select certain rare earth elements and so forth, right? Like so that's why for me, like it being able to have a solution with these rare earth element mixture and then run it through different ion exchange membranes and then analyzing the mixture, in the starting and also on the other side, right? Like again, I'm not looking for parts per billion, you know. I don't know if I'll end up being in parts per million. I don't know, but definitely parts per thousand. If I can get to a parts per thousand analysis and see what the concentrations are, I think I'll be pretty good with that. Like, is that something you think that is too difficult to do, or
No,
again, it's hard?
if you're concerned about some interference, because isobaric is one type of interference, there's all kinds of other interference. To get rid of it, you usually use the collision cells. So that's why you need a tank of helium. But but let me reassure you, you could use a tiny lecture bottle of helium, it'll last you a lifetime. It barely use any helium. You just need a one purchase of helium, and you're gone. You're
Oh,
good for life. So you use that as a collision cells, and what it does is the mass spec inject a little bit of that inside the instrument itself, and it kind of knocks out all the interferences. So you lose a little bit of signal, but you get rid of all the most of the interferences. So you could use that, and then you're on your way. You can do low pop a billion. That's not an issue at all.
what about chromatography? Is utilizing that with ICP, like first trying to separate it with that, and then is
So
there?
chromatography, you have to separate them based on the affinity with the medium that they're traversing the column, right? So it's possible. I've seen results, decent results, but the rare earth in particular, they're always bunched up together, right? They always give peaks really close to each other.
Well,
So,
well, no, I know a lot of, well, actually, no, chromatography is a primary method to separate rare earths. But I don't mean primarily like not only just for rare earths, like in general. Like, do you
oh,
see chromatography and ICP, utilized a lot, or is it like really rare cases? Like, would it help, doing that?
I see, ICP-MS. Yeah, I wish I tried that years ago. Well, I do this at home, so
Yeah.
I only have so much resources, but yeah, it didn't work out for me. But I've never used it, but professionally. But it's possible.
Yeah.
I mean, I know there's plenty of lab using it. I'm sure. Is it useful for lanthanides and rare earth mineral outside of research level? I don't think so. I could be wrong though, but
Yeah. No, I get. I mean, it's worth. I was just thinking about. I remember. I forgot what application I was looking at. If they're utilizing it, but it was some sort of chromat. That with mixed with ICP, and I was thinking, but like, I also kind of like, you do kind of dilute the sample a little bit, so like you end up, diluting the sample, which also kind of reduces your, whole
it's
analysis
possible.
cycle.
Anything's possible, but
Yeah.
just like everything else, how much money you're willing to put into it, and what is what's the uh what's the word I'm looking
Return
for?
on investment.
Right. What's the ratio of what are you going to get out of it versus how much you invested?
Yeah.
This is what it really comes down to.
Is there any other tips that you have on what's the best, that sort of thing, right? Like what's the best thing to focus on and try to optimize to try to get better performances?
So I know we talked about this before, but the digestion method is
Yeah,
really something to focus on, right?
because that's the biggest problem with ICP analysis is you need to digest the sample, right? It needs to be turned into a liquid. And that's a lot more difficult than it sounds. Like you just can't use hydrofluoric acid because it doesn't dissolve everything. It's the best one, right? It does dissolve almost everything, but there are certain things it can't dissolve. Um, and even just using acids directly, I see it all the time with, samples I get, materials I get, where you just try to use nitric acid on something, it doesn't work. But you use nitric acid in an electrolysis setup, well, it's able to produce oxidizing species that are so powerful that they're able to digest it, right? Fundamentally, how my leaching cell works, hydrochloric acid on its own doesn't touch gold, it doesn't touch platinum group metals for sure. But when you combine that with a very, very high oxidization potential, then you do, right? You can. Fundamentally, that's how they extract platinum group metals from catalytic converters. They use bleach and hydrochloric acid or liquid chlorine and hydrochloric acid. It's very dangerous. Please don't do this. If you're washing it, please don't do it because you produce very toxic chlorine gas. But it's the only way to do it because aqua regia won't even touch rhodium and platinum and so forth. So anyways, yeah, that's something I'd really like to see. What concerns would you have though in terms of that for the analysis? Would it simply to have too high of an oxidization, species? Would it have to be sort of reduced in some way to be able to run afterwards? Because fundamentally, as long as it digests everything, then it digests everything, right? Like, what because you said like in order to validate it, what concerns would you have?
Um, uh, it depends what you're looking for. So all the precious metals don't always behave the same way. The classic one is ruthenium and osmium. They have volatile oxide, right? So if you heat it up and try to digest it with an oxidizing environment, they're gonna leave the matrix, the environment, and evaporates away. So you're not gonna be able to measure them, and it's not exactly healthy to breathe. Some other ones might form absolutely insoluble precipitate that you will never be able to recover or react to anything. I don't have an idea in mind, case in point in mind, but you know what I'm saying. So it depends what you look for. So if you want to do a method for platinum, okay, use that for just platinum. You want to have one for gold and use that just for gold. Uh,
Well,
and
so the concern, the reason why this is such an important thing is because, this is a really huge dilemma and problem with a lot of miners. And there's this whole thing about, like, for example, quartz and there's gold, interlaced in that quartz structure. And there, obviously, if you're going to try to use Akurigi on that, you're not going to be able to dissolve the gold, right? Because it's inside of the quartz. So you have to be able to fully dissolve the quartz. So, in terms of that is more what I mean. And obviously, yeah, you're right. It heavily depends on the mineral structure and what you're exactly working with. But the goal is to be able to dissolve at least almost any mineral structure. Obviously you can't dissolve everything, because then what are you going to contain it in? Right?
so uh, gold has been studied probably a lot more than any other precious metals, and I think we talked about this before. There's a solvent, uh, just like with plutonium and uranium, the separation can be done with what is it, tributyl phosphate. Uh, for gold, there's another one. It's called methyl isobutyl ketone, I think, and it can selectively pick up gold from an acidic environment, and it's insoluble with or lightly soluble with water, so you can separate it pretty efficiently. From the test I've
Mhm.
seen, the research paper I've seen, it looked like it works. It's been done, but yeah, I mean, this is gold and gold alone. So what if you're interested in osmium? I don't know. What if you're interested in iridium? What if you're interested in all of them?
Yeah.
It's never been done. I don't think it has. I mean, I could be wrong again, but from what I've seen, man, nobody cares. Apparently, from what we had, the discussion we had is uh, precious metal industry is not so much like, hey, let's go dig into this mine to fetch rhodium. No, just oh, we have a zinc, a mine of zinc. Let's exploit the zinc and pump the crap out of it, and whatever we have in the tailing may have some rhodium in it. So, is it interesting to get in it? Is it financially, economically worth it? Don't know. Well, let's find out. Well, is it how much time and money? It's always coming down. We always come down to money. So uh, that's where we at.
Well, I think you said it perfectly is money, right? But also, is it worth it? because that's one problem I see all the time with every single technology and fundamentally ores, right? Like if there's platinum or rhodium in the parts per million, if there's just, in most cases they're in the parts per billion, right? And really good cases are in the parts per million, and like one or two. So if you have rhodium at like one parts per million, and right now, at its best price or whatever, I actually don't know what its price is right now, but it was like $150 per gram, right? So, 1 gram per ton that equates to about one parts per million. Um, that's $150 for a whole ton. So you have to somehow figure out how are you gonna use some of the strongest acids on Earth, which is able to dissolve rhodium, right? And do it economically at a whole ton. It's impossible. Like you cannot do that. Simply, producing any of those chemicals is incredibly expensive, and then shipping them across the state and utilizing them in the mine, and then trying to figure out what you're going to do with the waste and trying to neutralizing that waste. And right, it's so much expense to try to do it through a traditional process. It's impossible. That's the fundamental problem, right? Same thing with the quartz and the gold interlaced in the quartz. A lot of assay labs, if you ask them about this problem, they'll tell you, yeah, we know about this, but what's the point of measuring it? Like you said, right? They don't care, right? What's the point of measuring it if you can't even economically extract it? And I know this one laboratory in New Jersey, shout out to them. I'm friends with him. His name's Jerry, PTOE Services. But, he says it perfectly. Like, he provides these analysis to his clients, to his people, and then they ask him, okay, great, how do I mine it, right? How do I extract it? He's like, no, what technology? He's a little supporter of mine, but he's waiting on to see it, more commercially developed and stuff. But it's this weird thing. It's like, okay, great. Even if you go through the headache of trying to analyze it, what do you do next? How do you process tons and tons and tons of material, at these incredibly low margins? And that's where this technology comes into play. Fundamentally, the chemicals are derived from salt water and electricity. And then the oxidization species are generated at the highest potential possible because electrochemistry is, the best way to do that. And you do it all in situ on site and you completely recycle your chemicals. And it's absolutely amazing and incredible and so obvious, but it's never been done before because the membranes are so incredibly expensive and nobody would ever dream of, utilizing these very expensive, very fragile membranes on mining solution, which is, chemically the worst probably feedstock to deal with in chemistry. I don't know what your take on it is, but it's filled with all these elements, and very dirty and all this, and you have to try to figure out how to do anything with it. It's expensive, right? It's and exposing that to, these very delicate membranes, nobody's never wanted to do that. Because again, even if you do, then what? How are you going to economically utilize this in a scale if you're gonna have to replace these membranes and it's going to cost you millions of dollars to do so?
Well,
It's
that's where your process is important in a twofold. You if it works, then it's economically viable.
not yet.
But that's why it's important though, because it can open the doors to a different method for other processes. It could be economically profitable as well,
Yeah.
right? So that's
The hope that we all should be focused on is that by reducing the cost, you're also going to increase the supply. By increasing the supply, you're going to increase the demand. And at the end of the day, everyone wins at that. Let's be optimistic. Because there is definitely a lot of technologies though that they've been like platinum group metals, right? I would absolutely love to use them in hydrogen fuel cells or as in the catalytic properties, right? There's so many amazing things you can do with platinum group metals, but the cost and supply and it's just a headache. But it'd be like it's this technology really is. so amazing, so many degrees, because again, like if we, allow platinum group metals to be more readily utilized, and that opens up all these other technologies that use platinum group metals. But what's amazing is a lot of those technologies that utilize platinum group metals are the same technologies that need an ion exchange membrane. So, for example, a fuel cell, right, that requires an ion exchange membrane, but it requires platinum group metals to be able to convert and, gasoline into electricity, for
So
example, right?
platinum and yep.
Yeah, but so that's a good thing about my members was like great, right? They're cheap. They make fuel cells a lot cheaper to produce, but it still requires platinum group metals, and there are precious metals catalysts that you can utilize. But that also doesn't matter because now this mining technology is going to allow platinum group metals to be more readily utilizable. So it's this beautiful thing, that I see just in humanity, just entering this new age of prosperity where we're able to have all this amazing technologies. There's this other company recently that this one YouTuber covered, and I've been getting a lot of messages every day about. They're creating a thermo I forgot the name of it, but it's pretty much a thermal gradient a solid state fuel cell. So literally just by having a thermal gradient, it's able to generate electricity, very similar to a Peltier or a a Stirling engine, but it uses ion exchange membranes and is able to get really nice efficiencies, very low thermal gradients, relatively decent, size form factor. But if watch the discussions that the lead engineer has about the project and stuff, he says like the fundamental issue he has is the cost of these membranes. They're so insanely ridiculously expensive. So I'll try reaching out to him. Hopefully he'll be there's some sort of collab that can be done with that. But I just see so much beautiful things, with these membranes being done in almost every single industry imaginable. So thank you very much for people like you and Nighthawk and so forth who've they've covered it, right? They've given this technology a chance. That's it's yeah, it's gonna be a very nice. I call it the ionic age. That's the ionic age of humanity.
No,
And
you're welcome. If I can help anything at all from my limited knowledge and scope on the on the idea, of course, I'm more than willing to and happy to help. I think it has some potential. Uh, like everything else, I'm only human. I could be wrong. I could be misguided. So could you. But if we never investigate it, then what? We'll never know. What if?
yeah,
So no, I think you're doing a great work and you're passionate about it. It's heartwarming to see you being all up and going with it and sacrificing your time, your money, your family life. It's good. I think, and I hope it goes somewhere. And if I can help, then I'm more than happy to do that.
well, I greatly appreciate it. Thank you. I think the biggest thing that, because I've been this past like 3, 6 months, I completely changed my whole like view on this technology and the whole situation. One thing I realized is like getting the knowledge out, getting the awareness out there was my previous focus. And then what I realized the most biggest focus is education. There's so much education that's required for this. That's the hardest part that, doing simple stuff like this, teaching people the importance of analytical services. Like you do not understand like how amazing this video, at least I hope it'll be, that this video will be because there's this again, this is it's this thing that every professional in the industry knows the problems with XRF, but all these miners they don't. And I know companies that have lost millions of dollars because of they didn't know. And why don't they know? Because all these old big companies, right? They have their knowledge, they have their information, and they don't really care about sharing it. And it's resulted in this huge vacuum, but every single mine operation, is going through the same exact mistakes, learning the same exact problems. And again, they all don't want to share their information because they lost their money. They don't want, help someone else to not lose that money. But
Right, right.
it requires the community and people to start sharing their knowledge. Be like, hey, here's the mistakes I did so that you don't have to. Let's work together and try to learn and try to build together. So that whole thing is what I realized is, oh wow, that's a lot of work that's going to be required to re-educate all of humanity, to the importance of ion exchange members, the importance of technologies, the importance of industries, how they right now work and why they're very inefficient, understanding entropy and thermodynamics and fundamentally why, this is the most of it, like doing all that is so much work. My friend, he's been training me for this upcoming open source that I'll be attending, for a 30 second pitch that in 30 seconds I can explain to someone, what I'm doing, why it's so important. And, the first time we had a call, right, that was, I think we had like an hour plus long call and, I don't know how you felt, but I don't think you understood it immediately, right? I think that like after the second or third call, then you're like, oh wait, this is right. Is that fair to say? I don't want to speak for you, but
No, you're right. And then you told me about the Nighthawk video, which I watched, and then only after that was like,
yeah.
oh, that's what he said.
I have this problem with everyone. I mean, it's probably a flaw with me that I'm really a very bad teacher, but everyone I talk to, it's the same thing. It's like, it's not, even if I do my best in an hour or two, they don't get it. It takes literally weeks for them to get it, and so I
But
real
I think you dedicated enough, and you using as many social media as you can to try to get your message across, and I think you're doing the right thing. You're on the right track. Eventually, it's gonna pay off. Just I know it's we
Oh no
talked
no
about
no
this.
yeah yeah well, before I was a little like I'd say pessimistic about this whole situation. I'm like, oh, why don't, are, more content creators helping out or whatever. But then what, like, one thing I realize is, I'll try to keep this scientific. I'm not going to get too spiritual or whatever. But one thing I realize is, someone has to lead this technology, right? Someone has to lead the ionic age or whatever you want to call it. And I can't be relying on the cloud of other YouTubers or whatever to be the full, driving force of it.
Right,
Like
right.
what for example, one example, like I wanted to reach out to the open source society and other open source groups and try to, publish my technology there. And, I wasn't asking for any clout. I just wanted like them to start talking, them start utilizing, them just have a page on their Wikipedia and guides and stuff about utilizing ion exchange memories in their applications.
It's
And they all ignored me. They all didn't care. And I was again,
it's okay.
yeah.
It takes times. It takes dedication. Of course, you're gonna get ignored. It's just
Well, now I
look.
realize I need to create my own Wikipedia instead of relying on someone else's. I just need to make my own. Like
Well,
the community.
there's a great idea. Just do that.
Yeah.
Did you do it yet?
I'm busy with everything, but I do have a friend I talked about on my Discord server, and a great friend of mine. He created one for me. So yeah, that's exactly like that's the beautiful thing I realized of all this is like, it takes someone to lead this, and me giving me expecting someone else to lead this is the bad choice, right? I hope I'm please somebody lead this because I just want to have this technology. I just want to live in a world with this technology. But if nobody's going to do it, then I, I guess I will, and so, we'll see what happens. But yeah, I think that was one of the it happened very recently. It definitely happened in I'd say the last couple weeks, at least the last month. Where I'm like, okay, I have a lot of hard work ahead of me. And I'm okay with that. I'll go through it. And again, thank you
Nothing.
so much with people
Hey,
like you.
you're welcome. Nothing good come easy, right? As they say.
I don't even care about like again, this isn't about something good for me. This is just I genuinely just want to live in a world where we have flying cars, where we're not polluting the environment. That was the very first reason I open sourced this because I remember seeing how much this like every week there would be a new mine spill, a new dam filled with containment thing that was filled with this toxic mining acid waste that gets bursts and leaks into the a river and kills a whole river. This other community here, this community here, this community here getting destroyed by acid, mine waste. If you look into what's going on in Ghana right now, it's absolutely, it's sad. It's absolutely insane what's going on throughout the whole world. And, I realize like every single day I'm sitting on this technology and, not utilizing it properly for the whole world. Like, is another day that community is getting destroyed. So that's been my rush and my drive on trying to
Yeah,
push this forward is, you know,
yeah, I
um,
get it. I get it.
it's people with worse lives than me that, it means a lot to them too.
I know. But hey, you just like the rest of us, you bring in your small contribution to the rest of it, and I think I'm doing the same thing. I think Nighthawk is doing the same thing. Just bringing our tiny
Yeah.
contribution, try to help the big picture, right?
I hope the open source thing will be pretty good. I think that's also one thing is talking in person. I feel like in over the, because one thing that the Nighthawk thing taught me a lot was it doesn't matter how many videos I make or how many presentations I make, people will still think of me as a grifter or scammer or something, because it's too good to be true. It doesn't matter how it is, it's too good to be true. But if, being able to meet someone in person, be able to shake their hand and be like, hey, I'm a real person. I'm not some grifter and I'm not some scammer that's gonna, sell some crypto coin and then run out of here. No, like
Well, that's just like with everything else. If you have extraordinary claim, demand extraordinary evidence, right? As they say, who's it?
yeah.
Costing say. So you have to, prove yourself, and that's where I'm here to help to show that, hey, no, this
Yeah.
guy's on to something because look what I was able to get based on his results on his effluent. I was able to analyze it and show that blah blah blah. So I'm working on that. Keep on sending me your samples and I'll analyze them as I can, and
Yeah,
just be. It'll take time. Just be patient. We'll get there though.
could you firstly, how much more time do you have? I guess this is kind of getting a little long, but if you have a little more time, I want to talk about the samples that I sent you, if you have time.
Yeah, I don't have the results. Let me see. Yeah, what do you want to talk
Like,
about exactly?
ju- from my perspective, okay, those samples that I sent you, right? I ran them through my XRF and I got nothing, right? Because they were mostly lead. And lead with XRF is just absolutely horrendous. It just absolutely absorbs the X-rays, of course, because they
Right,
use lead
right.
in shielding. Um, but it's just absolutely horrible with X-rays because, it just completely hides everything. And as you see in this analysis you got, I had rhodium, I had this, and it was in the parts per million, which should have been in the detection limits, far above the detection limits of my XRF. And like that was when I saw that samples from you, that was like the biggest wake up call that I'm like, okay, I'm very critically limited on my analytical equipment.
All right.
Like
So, uh, what did you do? You remember what you got for? Oh yeah, you told me about
I
aluminum.
think
Yeah.
you did two, yeah, you did two runs. The first run was with aqua and the second run you tried with the sodium chlorate.
Oh, you talk about your not the pond, right? The
No, not yeah, not the pond, the
oh,
first
okay.
ones.
I don't remember those. Yeah, so for that, the only thing you can see is you had some ashes looking kind of sample. It looked like ashes to me.
After dissolving or before?
Well, the one you sent me,
Yeah, 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 yeah. Yep, yep, yep.
right? So, was it homogeneous? Was it uniform when you put it through the XRF? Was it any
It
clumps or any?
it was as it is, but again, it's
Yeah.
weird. It's because with X-ray, with XRF, like I know you mentioned a little bit on having a homogeneous sample, but it's spectrum overlaps also mean a lot because like also X-ray not only not only does lead absorb X-rays, but also if you look at the spectrum curve, it's like all throughout the whole damn thing. It's absolutely ridiculous. So what ends up happening is obviously you have overlaps that if gold's right here and lead's right here, because it's this so detectable and because it's all over the chart, you're gonna have one of the curves that just overlaps the peak for gold, or for example. That's the problem with that. But I mean, are you pretty confident on those samples at least? Were you yeah, I don't know what your thoughts on it, but like again, for me, being able to see that, there is platinum group metals was just absolutely huge for me because, I did have this other laboratory that did also analysis, and they showed, and I did my own chemistry test to see that I did platinum group metals, but being able to see the actual ICP analysis on something that I thought had nothing, actually did have something. was very nice, I guess. Does that make sense?
Was it the results I gave you, were they consistent with the other lab you sent your
No,
sample to?
there were a couple of different samples, so no,
Oh, okay.
there were a couple of different.
Well, all I can say is maybe the digestion involved in ICP measurement, it could have something to do with the difference with the XRF, because the XRF could have some matrix interference within it. Like if you have a bunch of sand left over, it, it could mask, I guess, some of the results being scattered all over your samples, versus when you digest it, you leave the sand behind. You only get your. I don't know, but it's
I can't again, I can't stress it enough. Like XRF just has, it's XRF, it's
it doesn't have a good reputation.
for a reason.
It,
Well, to be fair, I mean, it doesn't have a good reputation because, sample preparation. I didn't do it properly. The proper preparation for that case would have been to separate the lead firstly, at the very
yeah,
least.
yeah. So I'm sure there's an EPM method for that, and then it's good. XRF is good for qualitative. So, oh, there's some of this, some of this. Quantitatively, it probably all come down to your preparation. I've seen results from other labs with the same samples given OES, MS, and XRF. Yeah, they all, MS and OES got to come up with the same answer, but XRF is all over the place. So it's hard to say. Even though they were pretty uniform samples, I don't know what happened, but it's I wouldn't trust XRF. I mean, it's good to show, hey, here you go. Here's your one thing. Once you have matrix interferences and samples that aren't uniform as they should be, you deal with matrix interferences and all kinds of other crap I don't want to get into. But this is not too reliable. I wouldn't trust it personally. I wouldn't trust it. I could be wrong. I mean, there's plenty of
No,
people get good results from XRF. I never use it that much, and so
as someone
but
who's used it a lot, I don't trust it. Okay. It's good for, like you said, right? You put in a sample, you can at least know, is there silicon? Is there, in the percentage wise, right? You can at least know, maybe in the parts per thousand, but going below that, and again, it depends, right? You said, right? It depends on how you prepare. It depends on what the matrix is. Sometimes it can get accurate to the parts per million if it's done right, right? If you measure it off an existing standard calibration or another sample, similar type of sample that you already had calibrated for, and you already had an ICP analysis for, so you already know what that is, and then you measure what the difference is, right? If you do that, yeah, you can get to parts per million. But if you start putting in there random, powders and liquids and so forth that, is not what
it,
it's calibrated ready for,
it's a rough draw. Yeah? It's just like
yeah.
just
You're
throw
you're
everything
lucky. You're lucky to get into parts per hundreds or thousands. Is which
right.
is
I mean,
nice, right? Better than nothing. If you don't have any sort of instrument, at least getting into the parts, But also, I can't emphasize that enough. That's with this lab grade instrument, right? That's with me, placing in this cup and, because like it might sound stupid, but simply the height, right? The height matters because, of course, right? You have a beam that goes here and it bounces back into the detector. So if it's slightly higher, it's going to miss that detector and, it's going to scatter improperly and you're going to get, obviously like a prism effect, right? So you're going to get the wrong spectrum of that prism, if it's not in the simply the right height. Or you also said the, surface finish, right? If it's, like a loose powder, it's just going to scatter all over the place. And that makes a huge, huge difference, like when I got my training with, Rigaku with my XRF instrument, they it was a multi-day training session and they emphasized the importance of, surface preparation. And of course, it makes sense. Now, of course, I abuse it, right? I don't do proper surface preparation. I don't, set up the software, elements for exactly what's in there already. I don't do the proper steps. So, I get these, mistake results, but at least they're pretty, at least I get to the percentage accurate, again, the hundreds or thousands accuracy. But these handheld XRFs, like I can't stress enough how many times I've I've seen so many mines. They bring me samples and they're like, oh, look at this XRF results. It has 40% rhodium and 20% platinum and 30% palladium. And you add it all up and it's basically 100% platinum group metals, precious metals, and they're holding a rock. It's like, how does that work? How are you
Right,
holding a rock
right.
if you're saying it's all precious metals? And I run it on my XRF and it shows there's calcium and aluminum and silicon and iron. And it shows like how did their XRF miss that? So and the reason why is well fundamentally handheld XRF is a completely different instrument, right? It's only operates on
Maybe they give them a percentage of the higher ups. So if you disregard all the what's it call it the tailing, right? The silicate, all the low atomic unit.
No, that was the full spectrum. No, I've operated these equipments in person and no,
Oh,
there's a couple issues. Like first issue is, for example, is simply the mode that they put these on. A lot of times, so again, this is so if you ask these manufacturers of these handheld XRFs how to properly utilize them, what they'll tell you is you need to get a calibrated sample of the ore, right? And then you do the calibrate. Right? We already discussed about this. And if you don't do that, the best thing you can do is set it on certain modes, which already did some sort of similar thing. So, for example, you'll have XRF that specifically is calibrated on aluminum alloys. And that's all that mode is only good for aluminum alloys. It can measure between, aluminum, 6O whatever versus aluminum 2,
ah,
right?
yeah. I can see the problem already.
Exactly. And then they use that and then they put it on a rock. They're like, oh, look, it has, they'll put it on precious metal mode and then put it on a rock when it actually should be geology mode. And in
Where's
geology
your
mode,
problem?
exactly. So that's the first problem. But also, in the second problem is sample preparation, we talk about. But the third problem is the instrument itself. So, for example, this machine, right? It takes 10 minutes to do a single scan. It has a controlled height. It runs it through three different filters. Okay, so it actually has three different filters that it runs the X-ray through, the spectrum through to filter out the peaks. And it also runs at different voltages to excite different orbitals on the right on the molecule on the atom because there's different or electron orbitals so it can actually excite each individual to get a different spectrum chart. All of that combined together results in an actual analysis like the voltages and the spectrum peaks that they run on these handheld XRFs and they'll scan it for less than a minute, sometimes 30 seconds, and you just can't get any sort of data from that. A lot of times with these mines, they'll point it at an ore, for example, they'll hold it for 30 seconds, and once they see platinum, gold, or whatever, they turn it off. They're, oh, look, this is what I have. But
Yeah,
and you can see it on the top how long they've been, 30 seconds or whatever. But if you hold that same gun on that same rock and hold it for a good 2 or 5 minutes, even after a minute, spectrum's completely changed. And I have that in my XRF video that I, did a video on. Like I see this so many times with mines, they send me this picture. Oh, look at this results. I'm like, okay, use that same exact gun on the same exact settings, but just hold it a little longer. They're like, oh, what happened to the gold? It's yeah, so it's
yeah. You have to read the
that that
manual.
that's where education comes into play. Like again, you can't blame these guys because I thought of that the same thing before. I was in their shoes and I thought the same exact thing. So,
Yeah, it's look, every instrument have its limitations, and of course you have to read the manual before you use it to use it correctly and not get
well, the
in.
manufacturers also see, this is a little like slide thing, which, I'm not gonna say any names. But these manufacturers, they're kind of, they don't want these people to know how, like,
Well,
they want to be,
they want to
it's,
again, they want to sell instrument, right? And if you
yeah,
don't know how to use it and they barely tell you, then you have to pay for the technical support.
yes.
It always come down to the same thing.
Yeah, again the guy who funded me to buy this instrument, he wanted a handheld one, and you know, uh, because what you read on the brochures and on the on the marketing pages, like it's this beautiful thing that you point whatever. But then I contact the, sales team, and then I asked for their engineers, and I got specifically on a call with their engineers. They're like, oh yeah, no, 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 that's not how this works. But
Yeah.
then your marketing isn't correct, right? If everyone believes off your marketing that it's this magic thing, they just yeah, there you go.
You gotta make
So
money, man. It's just,
yeah, yeah, exactly. But hopefully, again, I think it's that don't think it has to be like that. It's a good tool if used properly, if you know how to use it properly, and
Yeah, oh
because
yeah,
it's
yeah, yeah, yeah. It gives you a good idea of what's if you know how to use it properly. It gives you a decent idea.
yeah.
If you want to get into trace metals, which is what you sound, which is what it sounds like you're trying to do, then yeah, you need an ICP, either OES or MS. My personal preference, like we talked about several times, is MS, of course, but yeah, the OES will give you a decent job.
Before I had this instrument, it was horrible. I do a refining, I do a process, and I have this gray looking metal, and I'm like, I don't know what this is. You
You
know,
know,
best,
uh,
and I tried doing acid separation or, acid, for example, a stannous chloride test, but, something similar to that. But for a lot of these platinum group metals, it's like a 20-step process just to verify one of these elements.
yeah. Well, as a rule of thumb for any analytical instrument, uh, the sample preparation and the injection method is 99% of the results, right? Because these instruments are pretty tuned, they're pretty good to go. Yeah, there's some details and stuff, but once you have a running instrument, if you have any problems with it, it really comes down to your sample preparation and the way you inject it, or the way it's being injected after you inject, the circulations and all the shit before it gets to the detector. That's 95-99% of the problems, if you have any problems. So once you get that done, you're good.
I, I
Most.
get a I get a lot of minds that ask me like, hey, what laboratory can we send it to, whatever. And a lot of times I tell them I don't know because, like you said, right? Like even if they have the instrument, do they know what they're doing with it? I don't know. And I've seen too many laboratories, national laboratories, that don't know what they're doing, right? They give a mass, analysis like, hey, there's this ounces per ton, this ounces per ton, this ounces per ton, and when you add it all up, it ends up to 100%, but there's no oxygen. It's like, how do you miss the oxygen? Like that's a really red flag. Like, how do you end up missing oxygen? Because rocks are 50% oxygen. Silicon is, iron oxide, right? Iron doesn't form as a solid metal, it forms as an oxygen. And how can you provide a company with a, ounces per ton analysis and you miss half of its weight? Like that's not a simple mistake. That's a really huge mistake. And, again, we all make mistakes, but, with
uh,
this sort of stuff, like, you
well,
know,
it depends. If you send a lot of samples to different labs, and they're gonna take a little piece of it and measure what they have in their own piece with their own instrument, and I could see this happening. But you're right. I mean,
who do you trust? How do you know to trust someone is the problem. That's the whole dilemma with this thing. Because like I said earlier, there's no mining industry, there's no refining industry, therefore there's no analytical industry. There's simply
right,
no
right,
one with the
right.
expertise and also the care to, right? Like, people don't even care. And I
I
know mines like that, they've spent millions of dollars just to set up their own laboratory space just to address this problem.
I agree. I saw the amount of problems and roadblocks I came across just to get a simple standard for rare earth and precious metals. Uh,
Is that
it's
something that you think I'll have, in trying to get ICP standards or?
Yeah, you absolutely need it. Yes, absolutely.
But is it difficult? Like, is it, is that something I could like call up Thermo Fisher and just get, or is that difficult?
No, you can get it, but
Okay.
uh, I mean, to me personally, it was difficult because I do this at home, and because of
Mm,
zoning, regulations, they're not going to send you anything. Oh, they can send a rich guy, tens of thousands of gallons of jet fuels to power their 747 in the garage, like John Travolta, but to send you a little bottle with 1 ppm of salt. Oh no, no zoning regulations, you can't have that.
yeah.
Where it's YouTube, so I'm just not gonna keep it PG. But you know where I'm going.
Yeah, yeah. No, I get you. I get you with that. Yeah. Okay, yeah, I was like worried if it was like, because with the cold rare situations, like it's even hard to get, some of that
Yeah.
stuff. So I don't know if that was like carrying over to the analytical side. But yeah, okay, so I guess we have some of the key points addressed, how difficult it is to do analysis, some background into XRF, ICP, refining. What do you see overall? Like, do you have interest in, doing analysis, or is there something that you like? What are your thoughts? What would you like hope for if you were to get into this?
Uh, I'm still trying to get into this. I don't have the real estate in my house and the equipment for that particular type of analysis, but I'm actively looking into getting uh, more real estate and more instruments. I recently acquired some extra stuff. I've been working with it, but again, it comes down to at this point right now, it comes down to real estate because I think I can get some instrumentations to
You
do
want to move
stuff.
down to Florida? I have lots of real estate. I have 5 acres. We can build a whole.
Yeah, but I still need to pay my bills, and
I know, I
there's
know, I know, I know. Yeah, hopefully soon, I've been saying that a lot though, but if there's an investor that ends up investing in this technology, that's something I'd definitely love, you'd be my first analytical guy to bring on the team.
well, of
Um,
course. Hey, listen, if you can get an ICP-MS before I can, then by all means, just call me up, and I'll come right down. And I'll help you out gladly. I'd be glad to help you
Thank
set it
you.
up. Show you how it works. Navigate the software if it's one I'm familiar with, but I'm sure I can figure it out if I'm not. Uh, and then
I appreciate that.
yeah, you're
Yeah.
welcome. No problem.
In the long term, I'm hoping to eventually get to Space Coast. I don't know if you're familiar with Florida much, but Space Coast, Brevard County, that's where they have their rockets and stuff. And because
Cap Canaveral and yeah,
yep, yep, because that's over there is the top of the tech right in Florida. That's where the top industries are. That's where the top leaders are,
of
and
course, yeah.
SpaceX and stuff. So, and also what's nice about that is all their subcontractors are also over there. So it's this really nice thing where I'm able to have this access to really nice talent and people, to properly develop this technology properly, to properly scale this up to what it needs to be because it's not just me. It requires great people like you. It requires other more people. I can't do that in the middle of nowhere, really. In where I am right now, I'm right next to this nature preserve, and there's nothing around me. Like, trust me. People always, when they come visit me, they're like, "Hey, you want to go? Is there a restaurant around you that we could go eat?" I'm like, "No, not really." It's not.
Nice. That's what I'm after.
I mean, no, I agree. It is nice. That's why I moved here, but it also like that's why I like Brevard County because they still have areas where like, undeveloped areas, but it's not this thing that you have to drive 1.5 hours to, a major city or whatever. It's, literally right there to Space Coast. So that's what I'm hoping. We'll see. That's when I have actual any sort of money and any sort of you know hour, but I'm working my best, and I think we've got at least at the very least I'm assembling a very nice team, like people like you, and I have other people that I've been joining on, helping me out, and they have injection molding experience and even product design experience and so forth. Like, these are really amazing guys that have really amazing experiences, and they all see the passion of this technology, and they're like, yeah, this is gonna be awesome. So one step at a time, one video at a time, and one big leap at a time, as
Yeah.
Sean did.
My grandfather used to say, patience, patience, patience. He'll get there.
Your grandfather sounds like a very patient man. All righty. I think that's a good note to finish off with. Or is there any other topics you want to discuss about, or any other notes?
Mm, not at the moment, but we can do this again anytime you want.
Yeah. Again, I really like this. I'll try, seeing if there's any other YouTubers because this is a really nice thing. A lot of other YouTubers, they have these sort of podcasts. I know William Osman and, William Osman, science, background science, Nile Red, Michael Reeves, they have their podcasts, right? That turn into open source, so This is a really good
So
thing. So
why are you wasting your time with a nobody that can be?
because you're the one that matters. You're the one that actually has analytical equipment. No, no, I'm not saying to do it with that. I'm saying to do with like a almost like an East Coast side, because all of them are on the West Coast, right? But I want like actually my friend, one of my friends, he's the one who reached out to me and reached out with hyperspace, connected us, and he's like trying to build this, community of YouTubers on the East Coast. So, again, I don't know. That's all. I'll try reaching out to, hyperspace or Nighthawk and seeing if they want to do, another podcast together, maybe the four of us or something, just nerding out because again, although today we did, a little bit of a presentation, but this was completely unscripted, right? Like, this was completely pure, unscripted, and
Correct.
we could nerd out about a lot of other stuff. I don't know about you, but like plasma physics or, flying cars or, space stuff or AI, right? A bunch of other things, just nerding out, right? That's what these people, do. That's what William Osmond and, they do with their podcasts. They just talk about anime and this, right? They don't talk about, exactly their, specialty every single time. No, they're human beings and they live lives and they talk about life. So hopefully
That's
we can
right.
do more of that.
Yep. All right. Sounds good.
Alrighty. Well, again, I
Thanks,
think,
Roel.
yeah, thank you very much, Neptunian, and hope to see you again.
You're
Okay.
welcome.
Bye.
Bye.